Portable generators are sold with bonded neutrals to comply with safety regulations for separately derived systems. Transfer switches typically do not switch the neutral because it is considered a common reference point and should not be interrupted. Isolating the neutral on a generator can be dangerous because it removes the protective bonding and can create the potential for electrical hazards. Rebonding the neutral for portable power use requires a separate device called a neutral jumper, which is not recommended for safety reasons. Bonding the neutral in both the house panel and at the generator may seem redundant, but it is actually essential for proper operation and safety. The neutral bonding at the generator ensures that the generator frame is safely grounded, while the bonding in the house panel establishes the neutral reference point for the entire electrical system. Stray voltage will indeed seek the shortest ground path. However, it is important to ensure that the grounding system is properly installed and maintained to prevent stray voltage from entering buildings or causing electrical hazards. The neutral is a common reference point for all electrical circuits in a system. Bonding the neutral at both ends, generator and house panel, creates a continuous path for current return, which is necessary for proper operation. Isolating the neutral can lead to voltage imbalances, ground faults, and increased risk of electrical shocks. For safety and proper electrical operation, it is recommended to maintain the bonded neutral at both the generator and the house panel. Isolating the neutral on the generator is not advisable. To elaborate further, let's explore the fundamental principles behind neutral bonding and grounding in electrical systems, specifically concerning portable generators used for home backup power. The neutral conductor serves as the return path for electrical current in an alternating current, or AC, circuit. It's typically connected to the ground at the main service panel, creating a reference point of 0 volts potential. This connection is crucial for safety and proper operation because it ensures that any fault current, such as a short circuit, can quickly flow back to the source, tripping a circuit breaker or fuse and preventing electrical shock or fire hazards. Portable generators, when used as separately derived systems, are required to have their neutral bonded to the generator frame. This bonding creates a similar 0 volts reference point within the generator itself. The purpose is to ensure that if a fault occurs within the generator or an equipment connected to it, the fault current has a clear path back to the generator, causing its overcurrent protection device to trip. Now consider the scenario where a portable generator is used to supply power to a home through a transfer switch. Most transfer switches are designed to switch only the hot conductors and leave the neutral conductor connected continuously to the home's main service panel. The question arises, should the neutral be isolated on the generator in this configuration? The answer, based on established electrical safety standards and best practices, is generally no. Here is why. Firstly, isolating the neutral on the generator would eliminate the 0 volts reference point within the generator itself. This could create a situation where a fault current doesn't have a clear path back to the generator, potentially leaving the generator frame and connected equipment energized at a dangerous voltage. Secondly, the continuous neutral connection through the transfer switch provides a common reference point for the entire electrical system, including both the generator and the home's wiring. This helps to maintain voltage stability and ensures that fault currents can flow properly, regardless of whether the power source is the utility grid or the generator. Thirdly, some propose that bonding the neutral at both the generator and the main service panel creates a parallel neutral path, which could lead to circulating currents or other undesirable effects. However, in practice, the impedance of the wiring and connections involved usually limits these currents to insignificant levels. Moreover, the benefits of having a redundant neutral path for fault current outweigh the potential drawbacks. Fourthly, the grounding system plays a critical role in electrical safety. Grounding refers to the connection of conductive parts of an electrical system, such as equipment frames and enclosures, to the earth. The purpose of grounding is to provide a low impedance path for fault current to flow back to the source, tripping the overcurrent protection device and preventing electrical shock hazards. When using a portable generator, it's essential to ensure that the generator frame is properly grounded. This can be achieved by connecting the generator frame to a grounding electrode, such as a ground rod, or by connecting it to the grounding system of the building being supplied. Fifthly, the National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. These requirements are designed to ensure that electrical systems are installed and operated safely. Article 250 of the NEC covers grounding and bonding requirements, including those for separately derived systems such as portable generators. It's important to consult the NEC and local electrical codes for specific requirements in a given application. Sixthly, when connecting a portable generator to a home's electrical system, it's crucial to use a properly sized and rated transfer switch. The transfer switch should be installed by a qualified electrician and should be designed to safely isolate the home's wiring from the utility grid when the generator is in use. This prevents backfeeding power onto the grid, which could be dangerous for utility workers and could damage equipment. Seventhly, it's also important to ensure that the generator is properly sized to handle the load being supplied. Overloading the generator can cause it to overheat and fail, and it can also damage connected equipment. Consult a qualified electrician to determine the appropriate size generator for a specific application. Eighthly, regarding stray voltage. Stray voltage refers to unwanted voltage that can appear on grounded metal parts of an electrical system. Stray voltage can be caused by a variety of factors, including improper grounding, loose connections, and electromagnetic interference. While stray voltage is not necessarily dangerous, it can be a nuisance and can sometimes cause equipment malfunction. Ninthly, to minimize the risk of stray voltage, it's important to ensure that the grounding system is properly installed and maintained. All connections should be tight and corrosion-free, and the grounding electrode should be properly sized and installed according to code requirements. Tenthly, regular inspections and testing of the electrical system can help to identify and correct any potential problems before they become serious hazards. 11thly, concerning the neutral jumper. The neutral jumper is a device that is used to connect the neutral conductor to the equipment grounding conductor. This is typically done in situations where the neutral conductor is not already bonded to the ground, such as in some portable generators. While a neutral jumper can provide a path for fault current to flow back to the source, it is not a substitute for proper grounding and bonding. In fact, using a neutral jumper incorrectly can actually increase the risk of electrical shock. 12thly, isolating the neutral on the generator is not advisable and can create dangerous electrical hazards. 13thly, maintaining the bonded neutral at both the generator and the house panel is generally the safest and most reliable approach. 14thly, consulting with a qualified electrician is always recommended to ensure that the generator is properly installed and operated. To further clarify the rationale behind maintaining a bonded neutral in both the generator and the house panel, let's delve into the fundamental principles of electrical circuit operation and safety. In an AC electrical system, current flows in a closed loop from the source, through the load, and back to the source. The neutral conductor serves as the return path for this current. When the neutral is properly bonded to ground, it provides a low impedance path for fault current to flow back to the source, tripping the overcurrent protection device and preventing electrical shock hazards. If the neutral is not bonded to ground, a fault current may not have a clear path back to the source. This could leave the metal parts of equipment energized at a dangerous voltage, creating a shock hazard. Furthermore, without a proper neutral to ground bond, the voltage on the neutral conductor may fluctuate, leading to voltage imbalances and potentially damaging equipment. Consider a scenario where a portable generator is supplying power to a home through a transfer switch, and the generator's neutral is not bonded to ground. If a fault occurs in an appliance connected to the generator, the fault current may not be able to flow back to the generator, as there is no low impedance path. This could leave the appliance's metal enclosure energized at a dangerous voltage, posing a serious shock hazard to anyone who comes into contact with it. On the other hand, if the generator's neutral is bonded to ground, the fault current will have a clear path back to the generator, tripping the circuit breaker and energizing the circuit. This is the fundamental principle behind electrical safety grounding. Now let's address the concern about having the neutral bonded at both the generator and the house panel. Some argue that this creates a parallel neutral path, which could lead to circulating currents or other undesirable effects. While it's true that there will be some current flowing through both neutral paths, the impedance of the wiring and connections involved typically limits these currents to insignificant levels. The benefits of having a redundant neutral path for fault current outweigh the potential drawbacks. In fact, a redundant neutral path can actually improve the reliability of the electrical system. If one neutral path becomes damaged or disconnected, the other path can still provide a return path for current, preventing a complete loss of power. Moreover, the continuous neutral connection through the transfer switch helps to maintain voltage stability and ensures that fault currents can flow properly, regardless of whether the power source is the utility grid or the generator. Now, let's discuss the role of the equipment grounding conductor, or EGC. The EGC is a separate conductor that runs alongside the circuit conductors and connects the metal parts of equipment to the grounding system. The purpose of the EGC is to provide a low impedance path for fault current to flow back to the source, tripping the overcurrent protection device and preventing electrical shock hazards. The EGC is typically connected to the grounding bus in the electrical panel, which is then connected to the grounding electrode. When using a portable generator, it's essential to ensure that the generator frame is properly connected to the EGC. This can be achieved by connecting the generator frame to the grounding terminal on the transfer switch or by connecting it to a separate grounding electrode. It's important to note that the EGC is not intended to carry normal operating current. It's only intended to carry fault current during a short circuit or ground fault. Therefore, it's crucial to use the correct size EGC for the circuit. The size of the EGC is determined by the size of the circuit conductors, as specified in the NEC Table 250.122. Furthermore, it's essential to ensure the whole connections in the grounding system are tight and corrosion-free. Loose or corroded connections can increase the impedance of the grounding path, reducing its effectiveness in carrying fault current. Regular inspections and testing of the grounding system can help to identify and correct any potential problems before they become serious hazards. In conclusion, maintaining a bonded neutral at both the generator and the house panel is generally the safest and most reliable approach when using a portable generator for home backup power. This configuration provides a clear path for fault current to flow back to the source, tripping the overcurrent protection device and preventing electrical shock hazards. It also helps to maintain voltage stability and ensures that fault currents can flow properly, regardless of whether the power source is the utility grid or the generator. While some argue that this creates a parallel neutral path, the impedance of the wiring and connections involved typically limits these currents to insignificant levels. The benefits of having a redundant neutral path for fault current outweigh the potential drawbacks. Consulting with a qualified electrician is always recommended to ensure that the generator is properly installed and operated.